In this session, we have to discuss on behavior of a geometric series. Here we have theorem. The geometric series summation n is equal to 0 to infinity x raised to n is equal to 1 plus x square up to infinity. The first condition is here this series converges if modulus of x less than 1. That means x lies in between minus 1 and plus 1. And the second condition is diverges if x greater than or equal to 1. And the third one is oscillates finitely if x is equal to minus 1. And the fourth one is oscillates infinitely if x less than minus 1. Proof of this theorem. Let Sn be the nth partial sum of summation n is equal to 0 to infinity x to n. That is equal to plus x square plus up to plus x raised to n minus 1. First case, when mod x less than 1, that is minus 1 less than x less than 1. So here Sn is equal to this one 1 plus x square plus x raised to n minus 1. So this is in geometric progression. So first term is 1 and the common ratio is x. So therefore Sn is equal to 1 into 1 minus x raised to n divided by 1 minus x. Next, that is equal to, so here we have 1 by 1 minus x minus x raised to n by 1 minus x here, because here the denominator is same, so that's why we have to separate the terms as 1 by 1 minus x minus x raised to n by 1 minus x. Next, so apply limit on both sides. Limit of s raised to n as n tends to infinity is equal to limit of 1 by 1 minus x raised to n by 1 minus x. So this is equal to 1 by 1 minus x, because so when we apply the limit, so x raised to n becomes 0, because here x is less than 1. So limit of x raised to n as n tends to infinity is equal to 0 if x less than 1. So therefore we get 1 by 1 minus x. So that means the sequence Sn is convergent. So that implies the given series summation n is equal to 0 to infinity x raised to n is convergent. Then case 2, let x greater than or is equal to 1. So in that, first we have x greater than 1. Now Sn is equal to 1 plus x square up to x raised to n. So here the first term is 1 and the common ratio is x. So here we have x greater than 1, this one. So that's why we have the formula a into x raised r raised to n minus 1 divided by r minus 1. So here common ratio is r, that's why that is equal to 1 into x raised to n minus 1 divided by x minus 1. Next, that is equal to apply the limit. So limit of Sn as n tends to infinity is equal to limit of x raised to n minus 1 by x minus 1 as n tends to infinity. So its value is infinity. So that means sequence Sn is divergent. That implies the given series summation n is equal to 0 to infinity x raised to n is also divergent. In next case, we have to take let x is equal to 1. So if x is equal to 1, then Sn becomes 1 plus 1 plus 1 up to plus n. So that implies Sn is equal to n. Next, limit of Sn as n tends to infinity is equal to limit of n as n tends to infinity. So when we apply the limit, so we get infinity. That means the sequence Sn is divergent. So finally we have the series summation n is equal to 0 to infinity is divergent. Case 3. So let x less than or is equal to minus 1. In that we have x is equal to minus 1. So therefore Sn is equal to 1 minus plus 1 minus 2 terms. So that is equal to 1 minus r raised to n divided by 1 plus r, or we have 1 plus r raised to n by 1 plus r. So this is according as n is even or n is odd. Therefore s to n minus 1 tends to infinity and s to n tends to minus infinity. S to n minus 1 is if n is odd, and s to n means if n is even. So that implies the sequence Sn is oscillates infinitely. So that implies the given series summation n is equal to 0 to infinity x raised to n is oscillates infinitely. So here we have one note, that is a geometric series converges only when its common ratio is numerically less than 1. And in next case we have let x less than minus 1. So x less than minus 1, that implies minus x greater than 1. So here let r is equal to minus x, then r greater than 1. So therefore r raised to n tends to 1 as n tends to infinity. So therefore s to n is equal to 1 plus x square up to x raised to n minus 1. So that equal to 1 minus x raised to n divided by 1 minus x, that is equal to 1 minus of, so here x is minus r raised to n divided by 1 plus r. So since x is equal to minus r, so the value of that Sn is that is equal to 1 if n is odd, and that is equal to 0 if n is even. So therefore s to n minus 1 tends to 1 and s to n tends to 0. That implies sequence Sn is oscillates finitely. So finally we have the series summation n is equal to 0 to infinity x raised to n is oscillates finitely between the values 0 and 1. So revision. So in this session we have to discuss about geometric series, and these are the reference books we have to use it in this session. So thank you very much.